Welcome again, everyone. I hope you have got stretched and had got your refreshment. Now it's time to start the last session for these 2 days campaign. This is the session 2 for today's presentations, and 4 papers will be presented in the session. The session will be chaired by Mr. Saeed Akhtar. Mr. Saeed Akhtar is currently acting as a General Manager, Reservoir and Petroleum Engineering at Orium Petroleum. He holds a BS degree in Petroleum Engineering from UET Lahore. He has been associated with oil and gas industry for last 32 years. Having a diversified experience in reservoir management, reservoir simulation, asset evaluation, techno-economic analysis, field development, its planning, well testing, production optimization, and well operations. Prior to joining OPI, Mr. Saeed has also worked with multiple companies like OGDCL, POL, GHPL, PEL, Divan Petroleum, and Spud Energy Private Limited as well. I would like to request Mr. Saeed Akhtar to please come on stage. Joining him as the co-chair for this session will be Fahim Razak Awan. Mr. Fahim Razak Awan is currently working as the Manager Reservoir Management at Mari Petroleum Company Limited. He is mainly responsible for the asset management of Mari gas field, which is the largest gas producing field in Pakistan. He holds a master's degree in petroleum engineering from Hertford University, UK, and an undergrad degree from NUS University as a mechanical engineer. He has been associated with oil and gas industry for last 2 decades with his expertise in integrated reservoir studies, asset management, enhanced oil recoveries, reserves evaluation, reservoir performance, its prediction, project management, and production optimization. Prior to joining Mari Petroleum, Mr. Fahim Razak Awan has a diversified experience while working for prominent organizations such as Halliburton, Talisman Energy UK, Repsol Sinopec UK, and Apache North Sea UK. His contributions has been instrumental in extending the life of the field and maximizing recovery from major North Sea oil fields, including Piper, Forties, Claymore, and Tartan. I would like to request Mr. Fahim Razak Awan to please join as co-chair for this session today. In this session, as I have mentioned before, 4 papers will be presented. So the first paper which will be presented today will be by Sprint Pakistan, and the title for the paper is High Rate, High Volume, a novel technique for uniform metric stimulation of naturally fractured low pressure reservoirs. Paper will be presented by Haroon Rashid. I will request Mr. Haroon Rashid to please come on stage for this presentation.
Hello everyone. My name is Haroon Rashid. I'm working as Senior Engineer, Coil Tubing and Stimulation in Sprint Oil and Gas. As by the name of the topic, I'm going to present a novel technique, high rate, high volume, as a metric stimulation technique in low pressure naturally fractured reservoirs. It is actually a case study in which we have utilized this technique and get most optimized results. Since this technique was kind of a modification in upcoming wells, we have performed conventional technique in the previous wells but didn't got results as we were expecting. But with this modification of utilizing this high rate, high volume technique, we got multiple folds of increment in the production. So the objective of this presenting this paper is we have naturally fractured reservoirs which like the depleted fields or the low pressure reservoirs in Pakistan as well, where we are utilizing conventional techniques. So we need to focus on the data where we are utilizing the conventional techniques and need to switch towards this new technique to get optimized results in terms of production. This is the flow of presentation. First, we'll see the objective of metric stimulation and the challenges we face in low pressure reservoirs. Secondly, we'll see the different asset placement techniques. Then we'll see the details of the case study in which we'll compare the job execution, stimulation results, job execution graphs, and the post-job results we got from both of the offset well data and the wells after utilizing the modified technique. The objective of metric stimulation is to mitigate the pressure drop arises due to skin to increase the productivity of the well. The metric stimulation technique gets challenging technique when we are performing it in naturally fractured low pressure reservoirs, since there, if we have, and it gets more challenging when we have high permeable zones in terms of heterogeneity and the permeability of the different streaks in the reservoir. So that high permeable zone acts as a loss zone and gets the injectivity of all of the treatment fluid in it without going into the low permeable zone, which jeopardizes the objective of the treatment metric stimulation job. So what we need to do is to divert this the treatment fluid of lossing in the high permeable zones, and it needs to go into the low permeable zone. So we need to divert this treatment fluid. For this diversion, we have different acid placement techniques. First, we can use a mechanical technique by utilizing a bridge plug or any kind of packer or combination of both, by which we can plug the high permeable zones and then pump or inject the treatment fluid into the low permeable zones. Another one is the coil tubing, where we can place acid at our desired depth. Also, we can utilize different kind of BHAs for which for different depth of penetration as well. With this technique, we can have a safety factor as well, by which we can say by hindering the flow, the treatment fluid by avoiding the contact of treatment fluid with the completion. Next one is the ball sealers, in which we pump cylindrical shaped small balls made up of solid nitrile coated with aluminum in the well, which resides in the perforation tunnel, and divert the upcoming fluids towards the low permeable zones. After that, we have chemical diversion and the foam-based diversion. The chemical diversion involves the changes in the chemical properties of the treatment fluid, like viscosity. We can increase the viscosity of the fluid, by which when it gets injected into the high permeable zone, it provides hindrance to the upcoming fluid, and the upcoming fluid can get injected into the can go to the lower permeable zone. Foaming technique is similar to the chemical diversion technique, where we introduce a foaming agent in our treatment fluid, and that foam, which creates the treatment fluid, which creates a foam type mixture of the treatment fluid, and that foam has high surface area. That surface area is going to provide hindrance for the injection of the fluid in the high permeable zone, and the upcoming fluid can go to the low permeable zones. The last one is the high rate, high volume technique, which we are presenting. Is in high rate, high volume technique, we inject the fluid at rates above the injection rate of the permeable zones, so that it can provide a scenario like a bottleneck, where we are injecting the fluid in the high permeable zone, and it goes to the the upcoming fluid can go to the low permeable zones. Now we'll see the details of the case study, in which first we'll see the fluid selection, that how we have selected the treatment fluid for the metric stimulation job, which consists of two laboratory tests. First is the solubility test, and second one is the reactivity test. In solubility test, we have performed test with the formation cuttings in two acid systems. The fluid selection for the formation cuttings sample was considering limestone, so it was HCl based acid system, and we have performed two tests with two concentrations, HCl 7.5% and HCl 15%. We get good solubility results in both of the acid systems. 7.5% was giving around 75 to 80%, and 15% was giving around 80 to 85%. Moving on towards the reactivity test, the reaction in 15% was more vigorous than the 7.5. Considering less than 200 degree Fahrenheit temperature, reservoir temperature, we have considered 15% as our treatment fluid. We can opt for more concentration, but since to avoid any damage to the completion jewelry, since the well was old, so we have opted 15% HCl. Now we'll go through the details of the case study, the job execution. We have performed 2 jobs utilizing different divergent techniques, as we have discussed before. First, we have utilized foam-based technique, in which we have pumped the treatment fluid at 5.5 barrels per minute, achieving an injection rate less than 500 psi. The graph is showing that stable pressure is showing that most of the treatment fluid was got lost in the thief zone. Similarly, in the next well, we have utilized kind of an improvement to use the chemical divergent technique as well, by the combination of both, but the similar results were achieved, like the injection pressure was less than 500 again, and most of the fluid was got lost in the permeable zone. So we decided to move on further, and we have utilized the foaming agent technique, we have utilized the chemical divergent technique. What we can do is to increase the rate, and we have performed multiple simulations and achieved different invasion profiles, calibrated our simulation results with different data points, and got the simulation results of the well. So in the next well, we have performed simulation at high rate as well with chemical diversion, and low rate with chemical diversion. And you can see on the graph on right side, the invasion, as the invasion profile shows that most of the fluid is getting injected into the shallower zone of the reservoir, and that is the invasion we are getting with low pumping rates. When we have increased the pumping rates near to more than 25 barrels per minute, then we got the invasion. As you can see that it is nearly uniform, and the fluid is going through all the streaks of the reservoir. One thing we noticed during increasing the rate was the factor of friction factor. As we were increasing the rate, friction losses were increasing as well. What we needed was to achieve high bottom hole injection pressure actually. So as we were increasing the rate, we were not getting the increment in the bottom hole pressure, but the increment was in the friction losses. So to mitigate or to minimize this factor, we have utilized friction reducer as well. So we have performed an injectivity test with 4% ammonium chloride brine, and achieved 25 barrels per minute at around 3000 psi. This was the limitation set by the client for the surface equipment, and this was the rate we have achieved. And we have performed similar job on the similar rates and got increment in the production up to 3-folds. Like the well was producing previously at 1 million, and then it increases to up to 3 million. We have performed a similar job on another well where we have achieved an injection rate of up to 40 barrels per minute at 3200 psi. And the job was performed in a similar way with the combination of chemical diversion, and we got again achieved the increment in the production up to 3-folds. What we have done in both of these wells was the introduction of a pad fluid as well, a viscous fluid ahead of the treatment fluid, which get injected into the permeable zone first, which provides the hindrance to the previous upcoming fluid. And that fluid is also going to be injected at high rate, the rate at which is the more than the injection rate of the permeable zone. So this is the combination of different divergent techniques by which we have achieved these optimized results. And then we have lesson learned and conclusion. Like what we have learned is we have tried in 2 or 3 chemical divergent. First we have tried chemical divergent technique. Second we have utilized first we have foaming technique. Then we have chemical divergent technique. Then we have utilized the different combination of divergent techniques, which includes the high rate high volume, which is the dominating divergent technique in the case studies. So combination of these chemical diversion and the high rate, high volume technique provides better results. Second lesson learned was that the data from the offset well has significant importance, since what we were doing we were using the data and simulating the invasion profiles by which we get the optimized results. So analyzing the data and the data set of the offset wells is a critical point as well. Also, in achieving the high rate, the major factor hindrance in doing the high rate, high volume job is the friction losses we are encountering during achieving the high rate, and use of friction reducer in those treatment fluids gives us a decrement of 20% in the friction losses. In the last, I would like to thank my colleagues and my fellow seniors to providing me this opportunity to present this paper, and thank you all of you to spare your time and attend this session. Thank you so much. If you have any questions, you are more than welcome, please.
Thank you, Arun. Now the floor is open for the questions.
Assalamu alaikum. Mohsin from OPI. I have a question. You mentioned in your slides limestone formation.
Yes.
So what was the matrix porosity?
Metric porosity was around, to be honest, I'm afraid I can share this data or not, since it's the client data, but it was around near to 20%.
Oh, 20%. So what kind of viscous fluid you used in this technique for diverging? Is polymeric gels or?
Yes, what we have used was VES-based viscoelastic surfactants that has a kind of an amphoteric surfactants which gets viscous when the acid reacts with the formation material. Like it depends on the pH and on the chloride content. It depends on different properties. Like we can make it viscous by adding it in the HCl-based acid system, and when it gets react with the calcium carbonate, the pH is going to get increased. This increment in the pH is changing the properties of the fluid, and the fluid is going to be viscous. Also, is this fluid, this VES-based chemical diversion is non-damaging as well. It gets break when it comes in the contact with the hydrocarbons.
Okay, thank you.
I got one question. Was there any consideration for the frac pressure?
Frac pressure was around, I've shown in the...
Especially at the higher rates, what was your bottom hole pressure? How does that compare with the fracture pressure?
It was around 4,500 psi, 4,000 to 4,500 psi, but we were not able to achieve the fracture pressure, since by increasing the rate, we were achieving the surface limitation, and that surface limitation is major portion of that surface pressure was the friction losses. So we were not getting the bottom hole pressure equal to or near to the fracture pressure. Yes, we can achieve the fracture pressure, but we need to reduce the friction losses.
Okay, any more questions? Okay, one more, last question.
Yes.
Harun, thank you for the great presentation. Are these jobs performed in the cased hole or open hole?
Both of those jobs were performed in a slotted liner.
Okay, thank you, Harun. Very good presentation.
Thank you so much. Thank you all.
Very much. Okay, the next paper is on the role of temperature on the performance of in situ CO2 EOR, and the presenter is Saddam Hussain.
Assalamu alaikum everyone. Thank you. The title of my presentation is The Role of Temperature on the Performance of In situ CO2. I'm associated with United Energy Pakistan as Reservoir Engineer for South Indus Asset. The agenda after my presentation is I'll be briefly touch upon the in situ CO2 evaluation, the technology, and the objective of our study. And I'll be discussing or explaining the reaction kinetics and then I'll be jumping to the Gibbs-free energy, and then mainly I'll be discussing the numerical modeling of numerical modeling of a 1D lab model and a 3D model, and then some sensitivity analysis on the temperature, and then the key outcomes and the acknowledgement. Since we all know that the supercritical CO2 is globally well known as an EOR method, but there are certain challenges involved in the supercritical CO2 injection, such as the transportation and the high capex involved for the infrastructure, and more importantly, we need the so abundant source of CO2 for injection purposes, and all of these require high capital expenditure, such as like mainly if we are talking about the market like Pakistan, we don't have the more abundant CO2 sources. We require like high pipeline. If the CO2 source is like very distant, we require morely like very large pipelines, and then it will also require the infrastructure such as compression cost and the surface facility cost. But how to overcome these challenges? So the latest technique of in situ CO2, where we are generating the CO2 inside the subsurface by injecting some CO2 generating chemicals such as urea. There are some other chemicals, but for our case, we are utilizing the urea, which is a byproduct of ammonium carbamate. And then in the urea reaction, you can see that this is the urea, and then once it reacts hydrolysis, and then it generates ammonia and the CO2 inside in the subsurface. There are some kinetics involved with this reaction. Once this reaction is spontaneous, it's going to contact with the oil. Once it's contact with the oil, all of the CO2 that is generated inside the reservoir, it kind of partitions or dissolved into the oil, and then the ammonia, that is another byproduct of this urea reaction, it generates the in situ surfactant in the reservoir. So there are two synergetic mechanisms, mainly two synergetic mechanisms that are involved in this kind of EOR technique. One is once the CO2 is partitioned into the oil, it swells the oil and reduces its viscosity, which even in the end it will increase the mobility of the oil and kind of also reduce the interfacial tension by mobiling the capillary trapped oil. And another added synergetic mechanism of this technique is the wettability alteration by generation of in situ surfactant with the help of ammonia. So the objective of this study, we initially evaluated the reaction kinetics. How does the urea behaves under certain pressure and temperature condition? How the urea reaction is impacted by different temperature conditions, and then the different chemical models that are built to evaluate the chemical potential of the urea in order to see at what temperature the urea will be spontaneous. It's going to generate the CO2 and ammonia. On the second side, and after that, after evaluating the urea reaction kinetics, we history matched our 1D lab models. There was some core flood experiments available, so we history matched that models and then upscaled our 1D model to the 3D model with the help of by building a quarter 5 spot model, and then see in order to evaluate how does this technique behaves under a subsurface environment at different urea concentrations and different injection rates and different injection temperatures. And at the end, we ran some sensitivity analysis on the temperature by keeping the objective function of maximum recovery that we can get with the lesser urea injection. So in order to evaluate this technique, we need to understand its kinetics first. And for the first thing is how does the CO2 is behaving or partitioning into the oil. That is based on the partitioning coefficient. We all know that the CO2 once it injects in the subsurface at higher pressures, it more like behaves like a liquid and its density becomes higher. So once the CO2 is generated under the reservoir condition, and then this CO2 is going to partition into the oleic phase or the oil phase at reservoir conditions. And then this partitioning oil will become swell and will reduce the viscosity. And the reaction kinetics, we computed the reaction kinetics based on the Arrhenius model, and there were some previous researchers who worked. They worked on the reaction kinetics of the urea, such as Kai et al., Sahu, and some other researchers who computed the reaction kinetics at different reservoir at different temperatures. And we see that the higher the temperature, the higher the urea reaction kinetic is. So in order to evaluate that what will be our temperature envelope for different reservoir conditions, like at different viscosities, different temperature conditions, how does this urea is going to behave under in terms of the simulation. But because in the analytical working, it shows that the higher the temperature, higher are going to be the reaction kinetics of the urea. So you can see that at the table below, these are the activation energy and the pre-exponential factor that were computed by different researchers at different temperature conditions. You see that at the higher temperatures, like 140 and 300, you see the activation energy becomes very high. And once the activation energy becomes very high, since this urea hydrolysis reaction is an exothermic reaction, and it kind of evolves like all of the heat into the system. So after that we computed the Gibbs-free energy of the reaction, because this is going to tell us the chemical potential of the reaction, because we must know that at what temperature this reaction is going to be activated or this reaction is going to be spontaneous. So it is the Gibbs-free energy model that gives us the direction of the reaction. And in this model, it tells us the change of enthalpy and entropy of the reaction of the reactants and the products. And once the Gibbs-free energy of the reactants is become greater than the reaction energy Gibbs-free energy of the products, the reaction is become spontaneous. And on the right hand side, you see this picture. It shows that at the almost 70 degrees Celsius, this reaction is become spontaneous. So after that, once we increase the temperature, this reaction is going to be higher and higher, and we will have more and more CO2 into our reservoir. So after that we history matched the 1D model. We estimated the 1D model. There were some core fluids available, and these core fluids were based on the post water injection. And you see that this is the residual oil saturation after water injection, and the residual oil water saturation was around 28%. We injected around 8 pore volumes of the brine in urea in different intervals. Like you see here, initially you see there is a small reduction in the residual oil saturation. That is because we injected the urea at this interval, and then after that we shut the injection valve in order to react the urea more and more into the reservoir and generate the CO2. And then after that, after the almost 3.5 pore volumes, once we opened the producer valve or the producer or the outlet side of the core, we said there is a lot of oil production. So what we concluded is that there were different kind of the synergetic mechanism that were involved, but the problem was we could not get the history match based on the reaction kinetics that were previously evaluated by different researchers. So that was another key challenge, and we modified the reaction kinetics in order to get the history match. So that was the part, and that was the equation that we built after the history match. And we all know that the mass transfer is kind of slower than the temperature transfer. So there were certain interfacial tension reduction effects as well because of the mobility of the capillary trapped oil. And then we also see there's a development of oil bank near to the producer as well. And after history matching, we quantified the recovery factor, that we saw that almost 10% of the recovery factor is increased based on the history match of the 1D model, and almost 12% of the oil swelled based on the reaction kinetics, and then approximately 70% of the oil viscosity is reduced through this method. And after that, we upscaled our 1D model to the 3D model, and we ran different sensitivities of urea injection at different intervals of time. We saw that we evaluated that when we are injecting the urea at initial phase of the life of the injection, we get higher and higher amount of incremental recovery. But when we because of the higher residence time of the urea inside the reservoir, but if we are injecting the urea at later part of time, we are getting some additional recovery, but that we are not allowing urea to get more and more time inside the reservoir and generate more and more CO2. And after that, we also evaluated that when we are injecting water initially, we are actually creating a cold bank near to the injector area. And after that, when we are injecting the urea into that similar injector, that urea is not going to react because of the colder bank near to the injector area. And so that's why we recommend that we, in order to rather than injecting cold water, we inject similar produced water inside the reservoir to actually reduce that colder bank near to the injector area. And also we sensitize some amount of urea that in order to optimize the cost of the injection of the urea. So we got the optimized results at almost 15% of the urea concentration that we injected. And also we used the real time or the real field PVT data and the geology data, but we did not use the structure of the data for this study. And after that, we ran some sensitivity analysis by utilizing the objective functions and some artificial intelligence as well. And we evaluated that almost like at 240 degrees Celsius, 2 degree Fahrenheit, we get the maximum result. But after that, our recovery doesn't increase. Rather, also we are increasing the reservoir temperature as well. So basically, it gives us the temperature envelope for this method. So initially, we evaluated this 70 degrees Celsius from the Gibbs-free energy, and after that, from the modeling, we are getting this 240 degree Fahrenheit as a maximum temperature for this viscosity of the oil. And also we evaluated that the almost 90% of the CO2 that is generated in the reservoir, it is dissolved into the oil. And another interesting fact was that when we modeled that 3D quarter 5 spot model, we saw that the majority of the CO2 that is generated in the reservoir is partitioned into the heavier components of the oil, because in the EOS system we divided our oil into 3 components, into the lighter components, medium components, and the heavier components, and in order to see where we have the major viscosity changes and major oil swelling for this through the in-situ CO2 generation. And we saw that we got the majority of the CO2 it is going to partition into the heavier components, and it gives us more and more recovery of the heavier components rather than the lighter components. So these are the key outcomes. We saw that the temperature envelope is mainly between the 270 degree and the 240 degrees Fahrenheit. The CO2 partitioning into the heavier component is another interesting outcome from this study, because it is going to help recover more oil from the heavier oil or the medium oils rather than from the lighter oils. And also we can utilize the produced water for injection purpose rather than the cold water, in order to have more and more impact of the urea generation because of this temperature effects. There is another recommendation from this study, is that if anybody wants to work on this, he can try this CO2 partitioning under different rock types, because we did not evaluated the heterogeneity and the different permeability or the different rock units for this method, and also different oil composition. This method should be tested under different oil composition. Although it gives us the results for the heavier components, but we should try it for the different oil composition in order to get this result, whether this technique should be applied on the variety of the reservoirs or not. In the end, I would like to acknowledge and thank UP management for allowing me to present and publish this work. And these are the references that are used in this study. And thank you, Mike.
Thanks, Saddam, for nice presentation. Now the forum is open for questions. We can accommodate only 2 questions.
Thank you very much. My name is Munib Virk from Mari Petroleum. Nice presentation, nice work. Just have a few questions regarding this. Do you have any actual field case study where this technology was applied?
Yes, there are
first question. Just let me 2 or 3 questions.
Okay.
Quick questions. The second question is, when you inject urea, after the reaction with water, how you are tackling the change in the mobility of water as well, and the change in the relative permeabilities because of the change in the nature of water, and its impact because of the water salinity, if there is any. And thirdly, have you considered the minimum miscibility pressures of the CO2 into your oil phase? Into the simulation, have you considered that as well?
Yes, starting with your first question was about the field case studies. Yes, there are some field case studies that are ongoing in US and in China as well, because this technique is mostly applicable to the water stripper wells that are producing at around 90 and more than 99% water cut, and they are converting into the injectors and injecting urea and getting more and more oil after that. There are some case studies available, and there are some recently published some case studies as well. I forgot to mention the paper number, so I can give you the paper number as well. After that, the second was about the urea, the salinity. Okay, so it doesn't change the water mobility so much, because this urea it's when we are injecting along with the water, it doesn't act like a polymer, because it doesn't have more heavier components into the urea. It just it's in the liquid phase, and once it contact with the reservoir and have the temperature effect, it's going to decompose into the CO2 and into the ammonia. So it doesn't have more time in order to actually reside into the reservoir or adsorb into the reservoir. But we need to check under different permeability conditions, that if there is a permeability is very low, so there will be challenge in order to actually pushing the urea solution into the reservoir and have this reaction activated. And third question was about the salinity. Yeah, miscibility. For our case, we kept the injection pressures above minimum miscibility. We computed the minimum miscibility pressure through equation of state. We had the laboratory tests available for the oil, and we developed equation of state model and computed the minimum miscibility pressure by injecting or by mixing different CO2 mole fraction and kind of evaluating where we have the maximum CO2 mole fraction injected and where we have the maximum oil swelling, and that we kept at the minimum miscibility pressure, and we kept our injection pressure above minimum miscibility pressure.
Saddam, nice work. You mentioned in your slides that reduction of interfacial tension.
Yes.
So have you calculated value of interfacial tension which you get after injection of urea?
So since it was, we did not have the validation from the laboratory method. So in the laboratory, it gives us the overall recovery. Okay, so we are getting 10% more recovery or 15% more recovery, but it doesn't quantify how much it is from the oil swelling, how much it is from the interfacial tension. So we during our 1D history match model, we kind of iterated this this interfacial tension by changing the relative permeability endpoints and getting the history match, get better history match. But there is for sure there is an interfacial tension effects as well, because if we are not changing the relative permeability endpoints, we are not getting this much of recovery. So yes.
Yeah, thank you. One more question. You in your slides you mentioned that after 70 degree centigrade that reaction becomes rigorous.
Yeah, spontaneous.
Fast, spontaneous. So you also mentioned the temperature graph with it. So does this mean that you have also injected the optimum amount of urea in reservoir? Because after some temperature, 240, 250 degree, the recovery becomes constant.
Yes.
So this means that that's the benchmark in which at which you injected volume of urea as well.
So we, for the 3D case, when we ran different sensitivities on the urea concentration, we got the optimum result with 15%. If we are injecting more urea, actually we are increasing the cost of the project, because urea it costs around, like it is around $3 per pound of the urea is the cost. So if we are injecting more and more urea, but that is particularly for this viscosity oil, like I mentioned, that is for 3 centipoise oil. If we have more like viscous oil, then I think the urea concentration might be higher or lower, because for this case the viscosity of the heavier component in our equation of state was around 15 centipoise, and there was majority of the CO2 that was generated, it partitions into the heavier component. So we see that this technique is more effective for the medium to heavier oils.
Okay, thanks, Saddam. I
Thank
think
you.
Mohsen can engage, Saddam in lunch time. Time is running short. I think we should go ahead.
Thank you, everyone.
Thank you, Saddam. It's very interesting work, I think. I hope this can find some practical application within local industry. I have a few questions I'll ask you offline. So the next paper is on improvement in drilling efficiencies by using mechanical thruster in BHA and long gauge bit. And this is being presented by Humad Muiz.
Assalamu alaikum and ladies and gentlemen. So let's start with the improvement in drilling efficiency by using the mechanical thruster. So unleashing the drilling prowess. In this presentation, we would discuss about how the technological advancement pushing the dynamics of the drilling engineering. So as we all know that the drilling operation is one of the critical operation lively going on, and the people's hierarchy from higher management to lower management putting the keen interest about every second updates. So sometimes the frustrations arrive of the low ROP, high stick and slip, high torque and unwelcome vibrations, which ultimately add the negative energy inside the string. So in order to mitigate those energies, we have introduced this tool inside the BHA to overcome those challenges and provides the desired results. Could you please move on? So secondly, I would acknowledge the authors and the co-authors of this paper and their valuable contribution to shape this paper to present it in this forum. On the left side, we can see there is a Cougar team, and on the right side, the Mole Pakistan teams. So their valuable time is appreciated to shape this paper to present it in this forum. Please move on to next. This entire presentation was structured around the following points. First, we would discuss about the introduction to the case studies. Secondly, we discuss about its schematic. Afterwards, we move on to its features, that how this tool works. And fourth, we move on to the placement analysis, that through working out some simulation, how can we place this tool inside the BHA for taking out its maximum efficiency. Then move on to some observations, and finally the results and conclusion. Next. So starting with the case history of this well, Mole well has been drilled Tarnaul 1 in 2022, Margla block, Pakistan. So drilling of Murray formation in 12-1 quarter-inch section, which compromising of interbedded lithologies, such the stingers of siltstone with sandstone in the massive clay stone. So what we have observed that the reduction of ROP and the increase in the stick slip. Multiple trips has been conducted with various bit types, but no improvement. As we can see, total 3 trips drilled from 625 to 3,600 meter with different parameters and applications. Obviously, there are some aggressive bits have been utilized. The 519 bits, the steel body bits, those are usually aggressive bits in this case, but ultimately the result is on the compromising side. So what the solution come up with us, the Mole team has delegate and strike their thoughts and their brainstorming that how could to mitigate this kind of vibrations and stick and slip issues. So while working on extreme side, we come up with the solution to deploy this tool inside the BHA so that we can reduce this with the weight on bit, optimizing with the weight on bit, and reduces the vibration at the over to pertaining a good ROP with the required strategy and interval. So before deploying it onto the BHA, there are some risk analysis has also been done, in which we have we collectively discussed with the Cougar team regarding its torque limits, their pressure drops issues, their through-bore ID of the tool, and it's if we are applying a jarring, so what kind of effect it can be seen. So overall the effects on the lower side, and further while discussing with its working principle and tool, I think Humayt will further discuss and gives you detail about the tool and its working principle. So Humayt, can you please? Thank you.
Okay, so this is a schematic of the mechanical thruster. Simple sort of tool, nothing very complex about this. The main thing where this tool, the main feature of the tool is in here in the spring stack. If you can see in the spring housing, that's where this is configurable, and this is what actually balances the compression against the pump open force or the differential pressure that is produced downwards. So once we apply weight on bit from the top, what happens is that the male spline compresses the spring assembly, the spring housing, the spring assembly which is in the spring housing. The spring housing has to actually balance itself, balance the weight on bit with the differential pressure which is produced below the tool on the bit. And resultantly, what happens is that as a result of this compensation, a consistent amount of weight on bit is applied on the bottom, and that produces that actually reduces the vibrations, and it also results in improvement in the efficiency of the drilling operations. There is one last part of the piston sub, just a simple compensation piston, and the function of that is to have sufficient lubrication to the spring assembly so that the springs do not get heated up and get failed. So that is just a simple schematic of the mechanical thruster. These are the features. So there are three forces that are acting on the tool when it is downhole. One is the compression, or the weight on bit. Then comes the pressure drop or the differential pressure, the pump open force that occurs below the mechanical thruster in the BHA. And the third one is the weight of the BHA that is below the mechanical thruster. All the components that are below the mechanical thruster, their combined weight. So these are the three forces that act. And all these three forces, these are balanced out by the mechanical thruster, by the spring assembly of the mechanical thruster to provide a consistent force to the bit at all times. The vibration mitigation, as a result of continuous force to the bit, what happens is that the axial vibrations and any stick slip that is produced by the bit, that is reduced, that is mitigated. So what the mechanical thruster does is that even if the stick slip is there, it will reduce any triggering of the stick slip to a certain level where drilling has to be stopped. So that's where this vibration mitigation feature of the mechanical thruster comes in. The mechanical thruster is configurable as per requirement. The spring assembly that is customizable as per the requirement, as per the BHA. It can be run with the RSS BHA, with mud motor BHA, any range of parameters. We can set the mechanical thruster springs in such a way to cater for the parameters in which it has to be used. The mechanical thruster by design, it is double thrust motion, upwards and downwards. So 12 inches of downwards and 12 inches of upwards deflection, it exists in this tool. So there is a double motion of both up and down. It's a through bore ID. There is very low pressure drop across the tool. The other thing, through bore ID, the spring assembly, which is the main part of the thruster, that is completely separated from the drilling fluids. So any type of fluid, LCM, any sand content, any solid amount, any mud weight, that is not going to affect the functionality of the tool, because the spring assembly is completely separated from the fluids. It doesn't come in touch with that. So any LCM want to pump in case of losses, that can be pumped. Even if an intervention is required, so that is also possible because the tool has enough ID. The tool up till now, it has more than 6,000 runs across the globe. First, it was used in North America. Even now, that is the largest market for this tool. Since this case study, which was the first time we used a mechanical thruster in Pakistan, we have used it with more clients as well. And there is a very low failure rate, just maybe 2 or 3 failures that have occurred. The other thing is that even if the spring assembly fails during the operation, it is not going to affect the actual operation that is happening at that moment. So no trip is required in case the spring assembly fails. Before running the mechanical thruster, we perform its placement analysis in regards to the proposed BHA and the parameters. This placement analysis is for specific this case study. So what we do is we put the mechanical thruster inside the BHA. The client provides us the parameters, the weight on bits, the pressure drops that are occurring below the tool. We put all of that data. We put the mud weight, we put the inclination that is there. And as a result, the other graph on that side, that shows us where the performance of the mechanical thruster is going to lie. So if the performance, if the curve is in between the limits of the mechanical thruster, the mechanical thruster spring assembly, so it's going to perform optimally. And that tells us that, okay, we can run this optimally and it will perform as per requirements. So this was the placement analysis that was run for this case study. And for every run, for every job, the placement analysis is run. And we cater it for as per the BHA and the parameter requirements. These were some of the case observations of this Thermol 1 drilled by MOL. So what we did was that we compared actually the runs in which mechanical thruster was involved and those in which there was no mechanical thruster. So since Azim actually mentioned that they were having an interbedded zone where there were stingers of siltstone embedded with clay and sand. So before the application of mechanical thruster, there was a lot of invisible lost time. Whenever there was a stick slip encountered, the BHE needed to be picked up, and then there was quite considerable time that was spent in reducing the stick slip and then tagging the bottom again. So with mechanical thruster, there was a reduction in invisible lost time. The vibrations were also reduced in the interbedded zone while using steel-bladed long-gauge PDC bit, which is an aggressive bit. The weight-on-bit application was good whenever weight-on-bit was required as per the formation drilled. So better weight-on-bit application was possible as compared to the runs that were previously performed without the mechanical thruster. The other thing that the steel body bit, it was an aggressive bit, 519 PDC. So it was expected that it might provide a better ROP, but the vibrations will also be there. But with the addition of mechanical thruster, it was quite efficient, and the remaining section was drilled quite efficiently. So these were some of the observations of the case. This is the post-job analysis. I will explain just briefly. The section started from 2148, 2150 meters. Up till 2948 meters, the performance was quite good. There were no limitations on the GPM or pressure limitations. After this 2950 meters depth, they started to get the interbedded zone with stingers of siltstone and claystone. And from 2948 meters up to 3600 meters roundabout, that is the zone where they tried to drill it with different parameters, different bits, but there was a reduction in the ROP. There was also a lot of erratic torque that was observed during this phase. The last phase from 3600 meters up till the end, that is when the mechanical thruster was added. So there was an improvement in the ROP that was observed overall if we compare all the intervals actually. Similarly, the weight on bit application as per requirement, that was better because prior to the mechanical thruster, they tried to increase weight on bit, as you can see in the upper portion, but in the interbedded zone. But they faced a lot of stick slip, so they had to keep it down. And similarly, the stick slip, they sort of remained almost the same, but considering that the steel-bladed aggressive bit was used with the mechanical thruster, so the vibrations were almost similar. So because of the mechanical thruster, we have this advantage. This was the final result. We compared the runs. Prior to mechanical thruster, the average ROP was 4.3 meter per hour. With mechanical thruster in the 3 runs, the average ROP was 5.9 meters per hour. So percentage-wise, there was a 37% improvement in the ROP. Final conclusion: the vibrations were mitigated with the enhancement of ROP, and this also allowed the application of aggressive bits to drill hard and interbedded zones with much better efficiency. That is all from us. If there are any questions, please.
Thanks, gentlemen, for questions, for a question session. I think time is short. We are really sorry. So we can accommodate only 2 questions.
First of all, very nice presentation, Farhan from PPL.
Thank you.
My question is regarding what are the surface indication of failure of these thruster, And in terms of money, how much you saved by utilizing this tool?
On the surface, if there is a failure, just like I mentioned, it is not going to hinder the operation that is going on. But what we can feel on the surface is that the vibration log, that is not going to be the same when while the thruster was performing. So that can be one indication which we can get from the real-time MWD logs. We can see a difference there. As for the improvement in the, can you comment on this, please?
Yes, as part of the ROP concerns, if you increase with the ROP, so ultimately the section which you are going to drill in 4 days, you can able to drill with the lower stick slip and vibrations, you can able to drill in 2 days. So you can overall see the impact of cost there. Ultimately, the services, rig time, all are the saviors for you.
Any more questions, please?
Mr. Humayt, it's very good technology, mechanical thruster. How can you relate it with the AST, anti-stalling technology? So if we compare both these two technologies, which one is good?
There are some tools that are used for the vibration mitigation. Other tools, they are on the market. But what I can compare with is that there is a tool, for example, by the company Tomax. Tomax is actually the same, that is the this stick slip tool, but they have a little limitation regarding when it comes to the mud properties, because our tool is completely separated. The spring stack, which is the main part of the tool, that is separated from the fluids. The AST tool, that has some limitations there. It cannot work with more than 1% sand. And similarly, there are some solid constraints and mud weight constraints with that. So there is a comparison with that. The other thing is that we have a 24-inch deflection up and down, 12 inches down, 12 inches up. Their tool is single acting, and that has a 7.2 inches deflection. So ours is more flexible, and it's both ways.
So you said that there is a separate path for drilling fluid in the BHA?
No, actually, if in the schematic, the spring assembly, which actually compresses or which balances itself with the pump open force, that is housed inside a certain spring housing, and that is completely enclosed, and no drilling fluid can go inside and affect it. So there is no effect of any type of mud fluid on the spring assembly. So it is not going to be affected.
Thank you.
Thank you, gentlemen.
Thank you
very much.
Thank you so much.
Thanks for nice.
All right, the last paper for the evening is Successful Integration of Channel Fracturing Unveils Promising Prospects in the Southern Region of Pakistan. It will be presented by Haris Ahmed Siddiqui.
Thank you. I may start. Okay. Good afternoon, ladies and gents. First of all, I'd like to thank the chairman, co-chairman, and all the ATC members present here for allowing me to present this paper. My name is Haris Ahmed Siddiqui, and I am representing SLB. So the topic today for the presentation of my paper is successful integration of channeled hydraulic fracturing, which unveils promising prospects in the southern region of Pakistan. This is basically a case study from Pakistan, including the 3 partners, mainly OGDCL and SLB, and then some JV partners from KUFPEC. Thank you. Let me go through the agenda today. So in my presentation today, I would go through the project overview, the challenges that we have and how basically we encountered and what solution we have proposed, including the phase strategy. And then finally, I would conclude my presentation by giving you guys the conclusion and the results, as well as the way forward. Starting with the project overview, as you all know, that oil and gas development company is one of the largest E&P in Pakistan, holding 75% of the interest. This is a case study of the second largest field after Sui, which is the second largest gas field, where we have the prospects to go through the candidate selection phase of a stimulation or the production enhancement. Basically, the stimulation technique of acidizing is already in place in this field. This is an old field which started and discovered back in 1990. And then there were multiple things that were going on this field to improve the production of the wells, while the hydraulic fracturing was unexplored or untapped in this field. So once we started to work on the candidate selection phase to come up with a production enhancement part, we started analyzing the old wells that were already being stimulated using the acidizing technique. But the main challenge here was to understand that, and to have a sustained production for a longer period of time for this field. Then the two main options came into play, which are the acid fracturing and the proppant fracturing. This is a carbonate formation. This is a limestone. Basically, moving forward, the comparison of the two technique and how we came up with the final decision of evaluating these for the proppant fracturing. The main two key parameters to differentiate between the acid and prop are basically the leak off and the longer length of the hydraulic fracturing. These are the two main points which were considered, and then based on the stresses that we experienced in this field, which I would discuss in detail in my next slide in the technical part, that the stress is higher than 5,000 psi. So the breakdown pressures here are higher, which makes acid fracturing a less feasible option compared to the proppant fracturing. So three main candidates were analyzed, and then one of the candidate with respect to the execution part as well was feasible and proposed to go ahead as a pilot well and to see how the proppant fracturing will act on this well. The main challenges that we faced were numerous, as this was the first pilot well that we are going to do it with the hydraulic fracturing part. Some of them are highlighted here, which include the absence of stress barriers, which is one of the major thing in terms of frag containment. So basically, the frag height is dependent on the stress barriers that we experience. Then the frag gradient ranges. Frag gradient basically ranges here from 0.73 psi per foot to 0.89 psi per foot. The breakdown pressures were a bit higher. So basically, the objective of the well is not drilled to the frag. So the completions were not mainly designed to contain these high pressures. So this is another challenge to propose hydraulic fracturing on this well. Which was taken into consideration during the candidate selection and ranking phase. And then lastly, the last thing is the completion quality. So we need to see how is our completion, how old is it, and will it be able to sustain the fracturing pressures that we are targeting. So as a solution, we proposed integrated workflow of 5-phase strategy. This include the feasibility study. In the feasibility study, it started with the construction of mechanical earth model, frag design, and then finally the production forecasting phase. So with the joint meeting, with the mutual discussion between all the partners and the shareholders that were involved in this project, we finally mutually agreed on the way forward and started with this integrated workflow. The first thing that we did was to come up with a feasibility study, which includes the construction of 1D MEM, which is a mechanical earth model. The main objective once to construct the MEM is to understand the stresses that we have in this area, to understand the rock mechanical properties like Young modulus, Poisson's ratio, and to have the overview of the pore pressure over the different layers of the formation, and how our fracture design will propagate. The second phase after doing the MEM part in this feasibility study is basically the frag design, which is the frag simulations. So in simulations, the main points that we are considering is basically the frag conductivity, and then the frag geometry, which is the frag height, frag width, and frag length. Finally, the third phase of our feasibility study is the production forecasting part, where we developed a simpler model, where we did the history matching of the well with all the production data that was available for this well, and we came up with pre-frag and post-frag profiles to showcase to all the partners that what we are going to do and what will be the result of this feasibility or the proposal of hydraulic fracturing. Finally, we presented the recommendation of this analysis and the feasibility study to all our partners who are involved, and then we mutually agreed on the way forward to let's do the hydraulic fracturing part and see how it proposed. So initially, due to the challenges with respect to the confidence on the technical data, as this was the first proposed well, we proposed to go with the breakdown injection part and the data frac to understand the technical parameters and the technical reservoir parameters, and then once we have the confidence on that one, we based on the analysis of the data frac, we move forward to the execution of the main job. You know, the fluid is one of the major component of hydraulic fracturing part where the lab testing comes into play. So the comprehensive lab testing was performed on whatever fluid is going to be pumped inside the formation and how will it be react. We have a district lab where we do the complete lab testing, and here you can see is basically the viscosity of the well doing the actual HPHT conditions on surface and understanding how our fluid will react with respect to the bottom hole conditions. Temperature log was recommended, basically the before and after the injection and the data frac part. This is to understand the frac height. Basically, since we have the absence of stress barriers, as I mentioned in one of the major challenges, so temperature log acted as to understand like how the fracture is propagating and what is our frac height. So here we saw that the fracture height was growing inside the formation, target formation layers. So basically this is helping us with respect to the production enhancement part in terms of sustainability. So this challenge was addressed in this way. Finally, we have performed the breakdown injection and the data frac, and the results were similar to what we had designed or what we have simulated in the feasibility study part, which is the closure gradient, the fluid efficiency, which we got was around 35 to 40% for the fluid. We somehow experienced the high height growth, and this is in line with our temperature log that we have found. But the good thing here for us to mitigate this challenge is that it's growing inside the layers which are in our target, and we don't have any water zone nearby on that part. Finally, we redesigned the well based on the analysis and that we got from the data frac, and we pumped the main frac without any issues. The total propellant that was placed inside the formation was 122,000 pounds of propellant with the maximum PPA in formation of 6 PPA. So that's how basically it was achieved, and the job was successfully and flawlessly executed, finally giving us the successful results in terms of production enhancement. So this well is producing from the last 6 months as expected, as per our expectation in the feasibility study production forecast, and this had given us around more than 2-fold of increase in terms of production enhancement. So this proved to be one of the successful cases of hydraulic propellant fracturing in the carbonate limestone formation in this second largest gas field of Pakistan, which was earlier untapped with respect to the propellant fracturing. Finally, I would like to conclude my presentation by giving the final basically thing on the approach or the strategical workflow that was adopted here in terms of the integration. So basically a multidisciplinary team was there, which include the reservoir engineers, the production engineers, and the hydraulic fracturing engineers. Starting with the integrated approach, sitting together with the partners, we improved the workflow, starting with the feasibility study, then different proposals on the data frac part, and then finally the execution of the main job, which proved to be a success for us. So these are some of the major elements, the improved workflow, and then finally the implementation of this technique. As a result, we implemented here was the technology that we have used is the channel fracturing, compared to the conventional, we have the higher operational efficiency. We have the higher conductivity flow channel because this technique involves the pulsation parts where our fluid is optimized, and then because of the pulsation we have certain other benefits over the conventional technique that is already being used globally. The placement rate in terms of screen out is better because of the pulsation and the drop in the hydrostatic in the column. And then as per the results, it's a better technology in terms of production enhancement as well, which is proven by the results that we have. Thank you.
Thanks, Haris. Floor is open for questions. We can accommodate 3 questions. The time is short, so please go ahead. Applause.
Thank you, Haris, for presenting and sharing the case study for this, the first pilot project well in Kadarpur field. My question is related to your conclusions. As you have stated that this well has been put on production for the last 6 months and 2-fold production. But what's the way forward for this well? So do we have to repeat the frac job in this well at after a particular interval, or seeing some parameters that has, if we see deterioration, or we have to repeat this frac job, or we have to go to conventional matrix stimulation for sustaining the production from this well? Thank you.
Thank you, Afraz Sahab. Very good question. So from the sustainability point of view, that's the main objective. So hydraulic fracturing, as we are aware that it's a quite basically the life of hydraulic fracturing is quite a longer period of time. So at the moment we need to understand the well, that how we quantify what damage are we experiencing. So basically for this field specifically, if we see that the production is going below par or whatever line we have set, then we can do the acidizing part to do the perforation wash to connect, or if there is any damage on the near wellbore part, we can remove that in that way. But this would obviously be a better option compared to the matrix acidizing that was being done previously on this field. Thank you.
Shah Jahan from Mol, Pakistan. You mentioned that there was not much stress contrast in the target zone. So was there any stress contrast available for the above formation, for example SUL and Ghazij, so that the height of the fracture can be constrained? And since the height of the fracture was quite much, so how did it impact on the fracture half length, and was there any impact on the productivity? Thank you.
Thank you, Shahjahan sir. Very good question. I was expecting this question. So basically, when we did the feasibility study, as I already mentioned, that this was one of the challenges that we faced, that there are no stress barrier. But the good thing here, which supported our case for hydraulic fracturing, is that the upper and lower, basically we have slightly higher contrast, which is basically stopping our fracture to grow over the target formation zone. So that's the best part here, which makes this candidate well a feasible option for the hydraulic fracturing. Now the second part, how does it impact the frac conductivity? For sure it is impacting our frac conductivity, because the height, basically in hydraulic fracturing, the main challenge is to control the height. And then this is one of the major challenge in this field, because of the absence of contrast or the lower stresses that we experience. But basically this is the part where I mentioned in my presentation, that we basically sit together with all the partners and showcase them that with this frac, with the simulation, we came up with the frac conductivity. So we have the frac conductivity that we are proposing in our design with respect to this, considering all these challenges that we have. Based on that, the production forecasting was done, and then the results were agreed that okay, fine, we are good to go with this one. This will vary obviously in this field for different candidates, well to well, but more or less we will experience the similar kind of behavior if the stress barriers are absent somehow. Then there are, I mean, the technique implemented here was there was the cost optimization part as well. So we don't have the option to go to the workover rig. If we have the option to go to the workover rig, we have other mechanical options available. Thank you.
Okay, thank you very much. It's a very good presentation, and it has given us some good understanding about the fracture in vertical well. But I feel that this productivity is not as much as encouraged, Unfortunately, fortunately, when people are doing fracturing, if the well was producing 1 million and it has produced after fracturing 1.5 million, there's a 50% increase. In absolute terms, the increase is not too much, about 1 million or 1.5 million is producing now after fracking, after this technique. My recommendation to the Kadarpur field, and we will discuss probably, that this has given us information about fracture conductivity and breakdown, all other parameters. We should be doing a horizontal well and doing a set of frac job to increase production by 2 or 3 4 times. So this well has given us indication that yes, the rock can be frackable, but horizontal well is the only solution here to produce a maximum gas from these tight reservoirs. So horizontal well should be designed, and fracking feasibility should be done on that wells rather than doing a vertical frac job, which is not encouraging. We want to increase from 170 to 270. The gas is there in Kadarpur. The only way is to do the horizontal well and then frac.
Thank you, sir. I would take it as a comment, and to add on that part, I do agree that obviously horizontal well have no comparison with the vertical well in terms of the reservoir contact area. So for sure, but the challenge, as I have mentioned, that this is an old field and these wells are not drilled to frac. So we have a challenge in terms of completions, quality, and the frac propagation part. So with all these challenges, basically, we come up with this optimized candidate well. Thank you.
Haris?
Very quick question, please.
Yes, very quick question. First, thank you very much for a very good presentation. I think I should commend you that limestone fracturing with proppant has been around for quite a few years, but in Pakistan, people have not tried it. And I think you have broken a mental barrier here, so I must congratulate you for that. My two questions, I have two questions, very short ones. One is about the proppant flowback. After you did you see any proppant flowback, and how did you manage it? That's number one. And then the second thing is, which is actually Dr. Saab's comment, it's just related to that as well, that the incremental cost and incremental production, how does the payback time work according to the incremental cost that you did because of incurred due to the frac, and then you had incremental production on the later? Thank you very much.
Thank you, Irfan sir. So basically, on your first question, yes, I do agree that in limestone, there are some cases, but we don't see much success in the proppant fracturing part. But yes, as our objective was to have the sustainable production, so basically this was the option that was available. And then from the cost point of view, in terms of cost optimization, basically here we didn't went for any workover part for specifically to this case study that I have presented. So that was one of the good point for us, for all of us, that our costs were optimized in that part, that we don't need to bring the workover rig, or the workover cost is saved in terms of that. And we did whatever was there. Basically this well was a very low producer and it was not going into the system, but now alhamdulillah it is producing well compared to the initial thing that it has. So that was the major point to present here in this, that from nothing it went to something. For sure, to give it sustainable and things like that, we have other options to consider, and then comment on that one, discussing it with all the partners, like how and what we can do on that part. Your second question regarding how we basically incorporated. So we sit together and we perform the economic analysis based on that, like what cost we are putting in this. Like without the workover, it's a relatively lower cost compared to the wells or the other candidate wells where we need to perform the different workover options like perforations or closing some perforations and then reperforations or some other method. So from that point of view, we sit together and we basically discussed with OGDCN and partners that how is it benefiting for us. And after agreement on that part, we went to do this. So that was in consideration.
Thanks, Aris.
Thank
you very much. Thanks for the time.
Thank you.
So with this presentation, it's the end of presentation sessions from this session of today. It's time to pay a little tribute as a token of appreciation to all the authors and co-authors for their hard work. Shields will be presented in a line with the pattern the papers were presented in this session. So the first paper presented in the session 2 for today is High Rate, High Volume, a novel technique for uniform metric stimulation of naturally fractured low pressure reservoir. Mr. Harun Rashid presented the paper, so I will request Mr. Harun Rashid to please come forward and receive the shield. Arif Yusuf, Ghulam Muhammad Waqas, Salim Saeed, and Jazeb Ali Bukti. In case of absence of all the co-authors, I will request the presenter to please collect the shields for them. The second paper presented today was from United Energy Pakistan Limited. Paper holds the title of Role of Temperature on the Performance of In Situ CO2 and Hand Soil Recovery. Paper was presented by Mr. Saddam Hussain. I will request Mr. Saddam Hussain to please come forward on stage. Zahir Ahmed, Mutafadil Murtaza Zakir, and Muniz Iqbal. The third paper presented was Improvement in Drilling Efficiency by Using Mechanical Thruster in BHA and Long Gauge Bit, a Case Study. Papers were presented by Humaid Moiz. I would request Mr. Humaid Moiz please come forward on stage. Shah Jahan Khan, Mohammad Asim, Zaman Sarfaraz, Waqasuddin. The last paper concluding this session was Successful Integration of Channel Fracturing Unveils Promising Prospect in the Southern Region of Pakistan. Papers were presented by Shlambarje Pakistan. I would request Haris Ahmed Siddiqui to please come forward and receive his shield. Syed Afraz Haider, Syed Ali Hasnain, Muhammad Sadiq Bal, and Nasir Hamim. After presenting shields to the authors and co-authors, now it's time to pay a little tribute to the chairman and the co-chair for the session today. For this, I would like to request Dr. Huram Zahoor to please come forward on stage and present the shields to the authors, chairs and the co-chair. The session was chaired by chair and co-chair by Mr. The session was co-chaired by Mr. Fahim Razak Awan. So with this, we end the entire two-day session for the technical paper presentations. I would like to thank all the authors and co-authors for their hard work and presenting papers here. We'll also thankful and great. I'm really grateful to all the audience for being so humble and sitting over here. Signing off from this session, Seher Malik.